Hi, I'm Rob Nosowski from Indiana University. This is a pre-recorded talk to be given at the 2023 virtual meetings of the Society for Mathematical Psychology. The work was done in collaboration with Adam Oath from University of Melbourne. Numerous studies have reported that there's enormous variability in how memorable individual images of real-world objects are. This memorability is often studied in tests of only recognition, in which observers are presented with lists of items to study, followed by test lists composed of old and new items. Certain old items are recognized with higher accuracy than are others, and people also tend to false alarm to certain new items more than others. There's a modern computer science literature in which researchers report attempts to build deep learning networks that can predict which images will and will not be memorable. Although these deep learning networks are interesting and impressive, a limitation is that they don't provide insights into the psychological reasons why certain images are more memorable than others. In addition, the deep learning networks tend not to be sensitive to the strong effects that context can have on memorability. Of course, there's a previous psychological literature that's also attempted to account for differences in individual item memorability. One approach that's shown some success involves the application of some similarity global familiarity models. In this approach, items are represented as points in multidimensional similarity spaces. Test probes give rise to a global activation of memory via a summing of similarity to the items in the space. The greater the sum similarity, the greater is the familiarity, and the higher is the probability that the test probe will be judged to be old. Here's a schematic sketch of the idea. The middle panel illustrates a list of 5 study items. The left panel illustrates an example of a target test probe. The target is a perfect match to one of the cats on the study list and is also similar to a second cat. Its sum similarity will be high, so the observer will tend to recognize it as old. The right panel illustrates a lure test probe that's also similar to the 2 study cats, although not an exact match to either. It too would tend to yield a high sum similarity signal, and observers might false alarm to this type of lure. The following slide illustrates some past data sets that I published, illustrating that this type of sum similarity global familiarity model can indeed yield very accurate predictions of individual item hit and false alarm rates. A major limitation of this past cognitive modeling, however, is that the experiments involve use of highly simplified perceptual stimuli and artificial category structures. Our goal in the present work was to begin to scale the models up and test their ability to predict memorability of a variety of real-world, high-dimensional objects. In this particular talk, I'll be focusing on our research involving rock categories as formalized in the geologic sciences. In particular, I'll be telling you about an experiment in formal modeling work in which we investigate how factors of category size, within and between category similarity, and presence of distinctive features influences the memorability of individual items. The stimulus materials in our experiment were a set of 240 rock images organized into 24 categories of 10 samples each. In the next few slides, I'll give you a feel for what the categories were like. To keep things visible, I'll just be showing you only 4 samples from each of the 9 categories, but you should get the idea. This slide shows 3 of the igneous rock categories. Each row is a category, and there are 4 samples per category. Here are 3 metamorphic rock categories, and here are 3 sedimentary rock categories. You should have a sense that items within each category tend to be more similar to one another than items between categories, but there's variation across the categories in terms of degrees of within and between category similarity. Each subject in our experiments are a single list of 75 study items. For each subject, each of the 24 categories was randomly assigned to a different category size condition. By category size, I mean the number of items from each category that appeared on the study list. There were 5 size 1 categories, 5 size 2, 5 size 4, and 5 size 8 categories. And there were also 4 size 0 categories that didn't appear on the study list at all. Following the study phase, there was the test phase in which we presented both old targets and new lures from each of the categories, and subjects judged whether each test probe was old or new. Our goal is to test the global familiarity exemplar model on its ability to account for the detailed old new recognition data in this real-world domain. I'll now take you through the series of steps that we followed to apply the model. Our first step was to embed the rock images in a high-dimensional feature space. We've used a variety of methods, but the main one has been to collect extensive similarity judgments among the rock images and to then use multidimensional scaling techniques for modeling the similarity judgment data. The MDS models have yielded good accounts of the data, and the derived dimensions have natural psychological interpretations. Based on a combination of good fit and ease of interpretation, here we'll be using an 8-dimensional scaling solution. In brief, the dimensions correspond to the extent to which the rocks are light or dark, coarse-grained or fine-grained, rough or smooth, shiny or dull, have organized versus disorganized textures, warm versus cool chromaticity, detailed aspects of their hue, and what we think are shape-related components. Having derived the MDS solution, we then apply classic laws for computing psychological similarities among the rocks. We use a Euclidean metric for computing the distance between any pair of rocks in the space. Then, following Shepard, we assume that similarity is an exponentially decreasing function of distance in the space. The steepness of the exponential gradient is described by a freely estimated sensitivity parameter C that provides a measure of the overall discriminability among objects in the space. A limitation of this classic model is that because the distance between any object in itself is equal to 0, all items have identical self-similarities equal to 1. Intuitively, however, it seems that some objects likely give rise to greater degrees of self-match than do others. We hypothesize that items with highly distinctive features that make them stand out from other objects in the set produce greater degrees of self-similarity. We apply a hybrid similarity model in which the presence of such distinctive features gives rise to boosts in self-similarity. To apply the model, we first collected a set of distinctive feature ratings for all 240 objects in the set. This slide provides an example of some rock images that receive very high distinctive feature ratings. And this slide provides an example of some rock images that receive low distinctive feature ratings. Let delta I denote the mean distinctive feature rating for item I. In the present hybrid similarity model, the self-similarity of an item I to itself was boosted by e to the beta 1 delta I. The similarity between item I and any other exemplar was reduced by the factor e to the minus beta 2 delta I, because any two random items are unlikely to share the same distinctive feature. Here, beta 1 and beta 2 are freely estimated scaling parameters. Finally, we substitute the computed similarities into the exemplar model decision rule for predicting the old new recognition probabilities. The overall familiarity F for any item I is found by summing its similarity to all the old study exemplars, and the decision rule then basically compares this overall familiarity to a recognition criterion parameter K. We fitted the models to the individual trials data of the individual participants by using a maximum likelihood criterion. The baseline model that does not make use of distinctive features estimates only 3 free parameters: the sensitivity parameter C, response criterion parameter K, and a gamma response scaling parameter that makes allowance for nonlinear relations between some similarity and global familiarity. The extended hybrid model adds the 2 distinctive feature scaling parameters beta 1 and beta 2. I'll now display a series of slides that show a variety of summary results and predictions from the models. This slide shows that false alarm rates for new items increase dramatically with increases in category size. This trend is reasonably well predicted by both models. As category size increases, some similarity of novel test probes to the study items increases, so false alarm rates increase. There's a much smaller increase in hit rates with increases in category size, a trend that is again well captured by both models. This plot shows false alarm rates and hit rates for each of the 24 categories themselves, averaged across the different size conditions. Both models do a good job of capturing the false alarm rates associated with the 24 categories. Apparently, some categories have greater degrees of within-category similarity than do others, and the greater the degree of within-category similarity, the greater is the sum similarity. There's not nearly as much variation in the hit rates as for the false alarm rates in these data. Nevertheless, you can see that the baseline model accounts for basically 0% of the variance in the category level hit rates, whereas the hybrid model is moving in the right direction for predicting the hit rates. Apparently, some categories contain members with more distinctive features than do other categories, and those categories tend to have higher overall hit rates. This slide shows hit minus false alarm rates for each of the 24 categories, which provides a rough measure of the extent to which observers could discriminate the old members of each category from the new members. Both models do a good job, but with a quantitative advantage for the hybrid similarity model. In still another analysis, we divided the 240 individual objects into 4 equally sized distinctive rating bins. This slide shows the mean hit rates and false alarm rates as a function of rated distinctiveness. You can see that hit rates increase with increases in distinctiveness, whereas false alarm rates decrease. The baseline model shows zero ability to predict the increasing hit rates, whereas the hybrid model does a nice job. Finally, in a rather ambitious analysis, we computed the observed and predicted false alarm and hit rates associated with the individual 240 items, averaged across the different conditions of the experiment. Sample sizes are small, so the results need to be interpreted with some caution. However, it appears that both models are capturing a major proportion of the variance in the individual item false alarm rates. The baseline model captures essentially 0% of the variance in the individual item hit rates. The hybrid model is starting to capture some of the individual item variation in the hit rates, but this aspect of the data remains a big challenge. We're currently exploring other factors that may account for this unexplained variation in the individual item hit rates, and I'll be happy to share some of our ideas during the question and answer period. In summary, using a minimum of parameter estimation in the present high-dimensional real-world category domain, a global familiarity exemplar model does a reasonably good job of accounting for major patterns of individual item older recognition performance. A key ingredient involves the idea that items with highly distinctive features give rise to greater degrees of self-similarity than do items without such features. The model accounts for effects of category size, within category similarity, between category similarity, and distinctive features on patterns of old new recognition performance. The model does a good job of characterizing patterns of false alarm rates at the level of individual items, but more work is needed to develop an improved account of individual item hit rates. We're currently examining other factors that may contribute to the variation in hit rates across the individual items. Thanks for listening.